VLSos here. This is a video lesson on slope field. A slope field is a graph of a differential equation. I'm going to write a differential equation, an equation that contains a derivative here. dy over dx is equal to x plus y. So this is an equation for the way a function y is changing. And that's all we got. But what if we were to graph what we've got? We would still have an x and y axis. What would we be plotting if we were plotting the way the y function changes? Well, we would be plotting a derivative at each location. So I'm going to need to choose values for x. But we're not going to calculate y based on that choice. We also need to choose values for y because we need both to calculate the derivative at that location, which is what the equation is giving us. That means that I need to choose a value for x and y and use the equation, in this case, add them together to get the derivative at that location. The location 1, 1 is here on the axes. And what I'm graphing is the derivative at that location. So how do I graph a derivative of 2? 2 is the slope of the tangent line 2y at this location. But I can't draw the entire tangent line with the slope of 2. I'm going to draw a tiny one centered at that location that looks like it has a slope of 2. And I'm going to keep my tangent line small because I'll be graphing many of them. At a different location, in this case 1, 0, the derivative is going to be the sum of the coordinates, in this case 1. The location 1, 0 is here. The derivative of 1, the slope of the tangent line 2y at this location, is going to be depicted by a tiny tangent line that looks like it has a slope of 1. New location, x is equal to 1, y negative 1. The sum is 0. So the derivative at this location, 1, negative 1, is 0. Tiny tangent line with a slope of 0 centered on that location. Let me keep x to be 1, and in this case, y is negative 2. Add these together, we have the derivative of negative 1. At this location, the slope of the tangent line 2y is negative 1. Tiny little tangent line, negative 1 slope. I'm going to look for the derivative at the origin. The origin has coordinates 0, 0. The derivative at the origin will be 0, depicted by a tangent line horizontal centered at that location. At some point, I'm going to be able to observe patterns. I can continue to choose values of x and y and graph the derivative at that point, but that would fill up a lot of information in the table. I'm going to graph a few more and then see if I can't observe the rest by patterns. If I choose keep x 0 and y to be 1, the sum is 1. So at this location, we have a derivative of 1. At 0, negative 1, the sum is negative 1. At this location, I have a negative 1 slope. I can see that if I've identified where the slope is 0, or the derivative is 0, and I go above it, then I'm increasing each time. So a slope of 0 becomes a slope of 1, and as I go up, the derivative increases by 1. Likewise, if I go down, the derivative is going to decrease. So if I have a 0, then a negative 1, I know it's going to be negative 2, and gradually more and more decreasing. My 0 slopes, the locations where the derivative is 0, is going to line up on this oblique. At this location, I have a derivative of 0. This location is negative 1, positive 1, the sum is 0. Above it, I will increase by 1, and going below this, I will decrease by 1 each time. So if I have a 0 derivative here, I can quickly complete more of these slopes by observing the pattern. I could fill the entire x and y plane with tangent lines which depict the slopes at those locations. We tend to only graph slope fields at integer locations because choosing too many locations to put tangent lines would fill it in, darken it in, and maybe unreadable. If it helps to graph a tangent line or the derivative at a non-integer location to clarify what's going on at particular places, that can be done. For instance, the graph in between 0, 0 and 0, 1, we could include to capture the nature of the differential equation at those locations. A slope field is a field of slopes. It's the graph of a derivative. A slope field captures the infinite potential or the infinite number of possible graphs of the equation y, because the slope field is working with only the way y changes. Let's do another one and get a better sense of this. Differential equation dy over dx is equal to negative 2y. We're going to make a table where we choose values of x and use the and values of y and use the equation to find dy over dx. In this case, we can observe that the equation does not include x. The derivative is only dependent on y. We can have an x and y axis, and I'm going to choose values for x. I'm going to keep it 1 each time. And I'm going to observe how the derivative changes at different places where y is changing from negative 2 to 2. The derivative is negative 2 times the y value. So if the y value is negative 2, then the derivative is going to be positive 4. That means that on the graph, with an x value of 1 and a y value of negative 2, the derivative is 4, or a tiny little tangent line that looks like it has a slope of 4. Filling out the t-table, the derivative with a y value of negative 1 is going to be positive 2, and then 0, and then negative 2, and then negative 4. I chose values of x to be 1 each time so I can see what's happening to the derivative just along this column in the graph. So at 1, 1, we have a slope of negative 2. At 1, 0, a slope of 0. At 1, negative 1, a slope of 2. And at 1, 2, a slope of negative 4. This is a pattern that will repeat for every x value. Because the derivative is not dependent on x, I could have chosen x to be negative 1, and these y, the derivative at each of these y values would be the same as what I've already drawn here. So I can observe the pattern and complete or fill in the slope field. Now, a slope field captures the infinite number of possible functions y, because all we know about the y function is the way that it's changing. That's literally what this equation is. But we can see some trends in what the y function looks like by observing the trend visually in the slope field. It might help to add more resolution to find the values of slopes in non-integer coordinates in order to visualize the trend a little more easily. In this case, we have a trend it looks like we have an intensely decreasing function, and as we get close to the axis, the slopes at these locations are showing us that whatever the graph of y must be, it must be slowing down and leveling off. Let's see another differential equation. dy over dx is equal to x squared. In this case, the derivative is dependent only on x. We're going to make a table and choose values of x and values of y and use the equation to find the derivative at those locations and graph them as a slope field. Since y does not affect the derivative, I'm going to keep y fixed at 1 and observe how the derivative changes depending on how x changes. I'm going to choose values that range between -2 and +2 for x. So the derivative at these 5 different locations are going to be the square of the x coordinate, or in this case 4, 1, 0, 1, and 4. So what I'm graphing is at y values of 1, which will be all those locations along this horizontal, different derivatives. At -2, we have a derivative of +4. And next value of -1, we have a derivative of 1. And 0, 1. And then at 1, 1, we go back to +1. And at 2, 1, +4. Now I can observe that this is a pattern, and it doesn't matter what the value of y is, this pattern in derivatives is going to be dependent on x. So I could choose a value of y is equal to 2 and get the same pattern of derivatives, which means that the pattern of tangent lines is going to be the same, again, no matter what y is, which allows me to quickly complete more of the slope field. Now, the slope field is depicting the infinite number of possible y functions. And to get a better sense of that, we can think of this equation purely in an algebraic sense and try to find the y function for which this is the derivative. That would require separating the y expressions by multiplying both sides by dx, and then integrating both sides to solve this differential equation, which would produce the integral of 1 dy is y, and the integral of x squared is x cubed over 3 plus c. The slope field is a graph of the derivative of this equation. It's how this equation changes. And this equation has a plus c, an unknown constant of integration, because there's an infinite number of equations that change this way. There's 1 for every possible value of c. So we ought to be able to see in the slope field the general nature of the graph of y, but not a particular graph because all of them are potentially correct. Now, the function x cubed divided by 3 is a modified cubic function, but x cubed over 3 is going to be a cubic curve. And we can see in this trend visually that if we follow these tangent lines, they are guiding us to create or to be able to visualize a cubic curve within. But where that cubic curve is can be anywhere up and down the vertical axis. Any cubic curve at any vertical position gives us an understanding that the equation y is cubic and unique at a vertical position dependent on the particular value c.